Hello everyone, welcome to all. In the previous session, we have discussed about uh, some basic introduction concepts regarding the what is the beam and the types of beams: cantilever, simply supported, or hanging. As usual, continuous or fixed beam. This is the looks like cantilever beam, simply supported beam, overhanging beam, continuous beams. Is number of supporters will be there. Fixed beams is means that both the beam which has both ends are getting fixed. Okay. These are the types of loads: concentrated point load, distributed load. Okay. If in case of point load, the diagrams will be look like, and UDL will be look like, and UVL will be looks like. Okay. So we have some definitions. First one is the reaction. This is the simply supported beam. Just replace the supports by the reaction forces here. How does this is the shear force conversion? What is meant by shear force? Uh, the algebraic sum of the force is written in section. The algebraic sum of the forces will be equal. Algebraic sum of, in the sense, the right side of the section will be equals to left side of the section. The shear force due to right side of the section will be equal to left side of the section. Here also RA plus RB equals to all the downward forces, all the upward forces will be equals to all the downward forces here. Okay, we are just considering here RA plus RB equals to F1 plus F2 plus F3. In case of bending moment, it will be looks like this one. Okay. uh, what any suppose we have a beam here, and at a particular point, the external forces will be there. Movement in the sense is force into perpendicular distance. So this force will cause a bending moment over a point x, or a section xx. Okay, over a section xx. Suppose we need to calculate the individual bending moments. Okay, due to the either RA or F1 or F2. Okay, due to the RA, we have a bending moment RA plus is multiplied by AX. Okay, this is the point A. And F due to the F1 is multiplied by Cx, F2 is multiplied by dx. Okay, here we just consider a sign convention. All clockwise direction will be positive, all anti-clockwise direction will be, all anti-clockwise bending moment will be negative. Okay, this is the counter point of counterflexor is nothing but the where is the bending moment reaches zero. Okay, or changes in sign convention, we can call it as a point of counterflexor. We will discuss along with the problems here. Okay, point of counterflexor. Shear force diagram, bending moment diagrams, nothing but the a graph showing the variation of shear force on the length of the beam, a graph showing the shear force along the graph showing the variation of bending moment along the length of the beam. You can call it bending moment. Okay, this is the same convention. Shear force will be, if you consider a section here, all the right side, for the right side of the section, all the downward forces will be positive. Okay, all the upward forces will be negative. Okay, if you consider the left side of the section, all the upward forces will be positive, all downward forces will be negative. Okay, suppose for the bending moment, this is the sagging. Okay, this is the type of deflection, and we can call it, this deflection in sign convention is positive. Bending moment, we can call it as a sagging, and then this is the hogging. This is, you can consider it as a negative. Okay, this is the procedure for the shear force and bending moment diagrams. Okay, so now in this section, we are going to discuss about the shear force bending moment diagrams for the cantilevers. Okay, for the cantilever only. Initially, we are going to, first point is uh, cantilever with a point load at a free end. At a free end. Okay, uh, it is looks like this one. Okay, at a free end, we are applying the a load of W. Okay, consider section xx at a distance x from the free end. From the free end at a distance of x, we are just considering a section here xx. Okay, shear force diagram. As shear force diagram, shear force at a section xx equals to plus positive only. Why? Because write down is positive. Write down is nothing but any shear force, any external force. Write down here. You just considering a section here. Okay. For the right side of the section, all downward forces will be positive. Okay. All upward forces will be negative. All downward forces will be positive. So that W plus W will be there. Over here, there is only one force will be there. Shear force. One shear force will be there. That's why I'm just considering a one W. Okay, and the sign convention will be positive. Okay, the shear force is constant between A and B. There is no load between these 2 points. Okay, you don't have any loads in between the AB. Okay, that's why reason the shear force will be constant. Okay, how do we represent constant? We just draw a simply a diagram, a horizontal line here. Okay, due to amount of load, the this is the A. Just to have a look at this one, we are just having a baseline. This is the baseline, and over which we have a raises to some height of W, which is equals to W. How much amount of W will be, which is equals to W here. Okay, and after that one, we have a constant load here. Okay, have a constant up to the fixed end. Why? Because there is no any point load will be in between these 2 points. Okay, this is the shear force diagram. So this is the positive. Okay, first suppose if in case of bending moment, we need to calculate bending moment at the section xx. This is the section xx. So bending moment will be minus W into x. Why? Because the clockwise bending moment is right is negative. If you consider, I'm just considering right side of the section. Okay, the bending moment will be due to the force will W will be clockwise. Clockwise in the sense the this force will be tends to rotate in their body in a clockwise direction. Okay, so that's why I'm just considering the negative sign. Now, how do we consider the positive? How do we consider the negative? Will be habitual by number of by doing number of problems. Okay, negative. So negative bending moment, negative W into L. Suppose at the point of x at the section xx, the minus W into x. If the bending moment is proportional to distance from the free end is nothing but the bending moment at x equals to 0. Whenever the x is 0, in the sense the bending moment will be at the point B. In the bending moment, so here the bending moment will be 0. Why? Because W into there is no load distance, 0 distance. That's why bending moment will be 0. Whenever there is a length of L, the bending moment will be W into L. It is negative. Okay, the bending moment will be represented like this. First of all, we need to draw a baseline here, AB, and that's I'm just we need to calculate the bending moment at the fixed end. Okay, minus WL. So that much of amount will be just noted here. Okay, and from here to here we just draw an inclined line. Okay, and this is the negative. Okay, just remember, whenever the shear force is positive, obviously there will be negative bending moment. Okay, whenever the positive bending moment, obviously there will be a negative shear force. Okay, quite opposite. If this shear force will be positive, obviously the bending moment will be negative. Okay, suppose what will happen is uniform the cantilever with uniformly distributed load. Okay, suppose cantilever with uniformly distributed load of W newtons per unit length of. Okay, consider section xx at a distance of x from the free end. Okay, here the UDL will be like this one. This is the cantilever beam over the beam. Throughout the length of the beam, UDL will be acts on the body. Okay, I'm just considering a section xx here, which is the distance of x from the free end. So this is the B is the free end. From the distance of x, we're just considering xx. Okay, As we know that for the shear force at the section axis, all the downward forces will be positive. Downward force in the sense W into X. Here, how do we represent the shear force in case of point load? How do we represent the shear force in bending moment? Uh, Shear force in the UDL. For the point load, the shear force will be same W. Okay. For supposing if in case of UDL, the load will be W into X. How much is distance of X? Okay. This is the X. Okay, W into X. Okay. Here force will be W into X. The shear force will be W into X. Since the variation of shear force follows the linear law. Linear law because in case of point load, the shear force will be straight. If in case of UDL, the shear force will be inclined line. Okay. Just remember this one. Okay. Point load will be, the shear force will be straight. If in case of UDL, the shear force will be inclined. Okay. If in case of point load, the bending moment will be linear. Okay. If in case of UDL, the bending moment will be a linear parabola, second degree parabola. Okay. This is the parabola. Okay. Here, what is the difference between the point load and UDL for the same cantilever beam? For the point load, the SFD shear force diagram will be straight line. Okay, positive. If in case of UDL, here also positive, but the inclined line will be there. Here the straight line will be there. Here the inclined line will be there for the shear force. And for the bending moment, here the inclined line will be there. Here a curve will be there. This is the second degree parabola for the UDL. Okay. How to draw for the BMD, bending moment diagram. If in case of before going to here, the variation of shear force follows the linear law. When x equals 0, shear force will be 0. As you know, there is a shear force in the sense at the particular, if x equals 0 at the particular point B. Okay, just to follow my cursor. Okay, at the particular point B, the x equals 0, there is no load. Why? Because here we have a load, but how do we represent the load W into X for the UDL? So here X equals 0. So obviously W equals to also 0. Okay. At the point B, there is a shear force. And at the point L, there is a shear force W into L. Okay. So we have a just to initially we have to draw a baseline here, and we just mark the magnitude of shear force on the right side of on the vertical, and from there to here we just draw an inclined line. Okay, inclined line. We just represent the units also. Here the WL, this is the magnitude WL of amount of shear force will be acts on them. Okay, here also WL square by 2. My amount of magnitude will be amount of bending moment will be there. Okay, we need to calculate the bending moment WX. How do we draw? Okay, to calculate bending moment in section X. Suppose I just first of all, let me consider a bending moment at the section XX. Okay, to calculate a bending moment at any X section, assume that total load due to UDL acts at the middle of the beam, loaded part of the beam. Therefore, bending moment at a section XX will be bending moment X equals to minus. Suppose what does it mean? Means that minus W XX by 2 is nothing but the minus W x square by 2. So how does it looks like? Bending moment in the sense of BH. The area will be of BH, of B into H, of B in the sense how does it behave? It become how does where it comes from? Suppose mm, We are going to explain the problem. So for the clarity, okay, for the bending moment, just remember this point here. Okay, remember this value. This is the W x square by 2. How does it comes? I will explain in the problematic point of view. Okay, if you understand in the problematic point of view, it will easy to for you. Okay, minus W x into x square. Just remember this one. I will explain. Definitely, I will explain. Okay, W minus W x square by 2. How does it comes? Okay, and the next one is the suppose if in case of any bending moment due to point load, the value will be W x square by 2. Okay, just remember the okay. Thus, the various of bending moment follows the parabolic law. So if in case of x equals 0, the bending moment will be 0. If in case of x equals to L, the bending moment will be minus W square by 2. Here the why negative sign will be there. Negative sign in the sense uh, negative sign in the sense um, here the all bending moment will be there. All downward forces will be negative, just like this one. Okay, this is the negative. Here negative. Okay, from bending moment it be 0 and it is increases to minus W square by 2. This amount of up to this magnitude, the bending moment will be various in the form of parabolic curve. Okay? This is the point load. This is the examples. Okay, just have a look at these examples here. A cantilever of 3 meters long carries a 2-point loads each 4 kilonewtons. One placed at a free end, other at 2 meters from the fixed end. Draw shear force and bending moment diagrams. So how to draw? So we have a draw data half a cantilever beam which is having a length of 3 meters. 2-point loads will be there. 4 kilonewtons at the free end, another 2 meters from the fixed end. From the fixed end, 2 meters. Okay, we have so two loads will be same 4 kilonewtons, 4 kilonewtons, 4 kilonewtons. One load will be the free end, one load will be the 2 meters away from the fixed point. Okay, so we need to calculate the before we need to calculate the shear force and bending moment diagram. Just have a I'm just going to explain the basic assumptions. Okay, how to draw shear force bending moment diagrams apart from the calculations. Okay, just remember my concept. Suppose just draw a baseline here, A, B, C. Okay, this is the baseline. So this is the baseline. Okay, uh, after the baseline, and just draw a upward direction up to the 4 kilonewtons. Okay, this is the 4 kilonewtons. Okay, and here up to here, from here to here, there is no any load. Okay, just draw a straight line here, straight horizontal line. Okay, and then later beyond that one more 4 kilonewtons will be there, will be adding to this existing system. Okay, from here to here one more 4 kilonewtons will be there. From here to here, from here to here, there is no any point load. Okay, there is no load, so the shear force will be constant. Okay, the total load will be at this point the total load will be here the 4 kilonewtons, here the 4 kilonewtons, the total will be 8 kilonewtons. Okay, here. Okay, it represents that at the free end the shear force will be 4 kilonewtons. At the point B, the shear force will be 8 kilonewtons, and which is constant throughout the length of the beam up to the free end, up to the fixed end. Okay, and here also how to draw bending moment diagram. From just draw, we need to draw a baseline. This is the baseline. Okay, A, B, C. This is the first one. Before going to initiate the SFD or BMD, we need to we need to calculate. We need to draw a baseline here. Okay, up to after the baseline, after drawing the baseline, from here to here 4 kilonewtons. So up to here 4 kilonewtons, the line will be here. Incline line will be there. Okay. And from here to here, 8 kilonewtons will be there. 8 kilonewtons in the sense 8 bending moment here. The bending moment will be there. Uh, here from C to B, the incline, some amount of incline line will be there. After that, one more shear force will be there. So due to when adding of one more shear force, it gets some deflected like this one. Okay, it gets some deflected. So this is not the straight line. This is not the inclined straight line. Okay, from here to here one line is there. From here to here another inclined line will be there. Okay, the just to observe this one. This is not the straight line. From C to B, we have a inclined line with respect to the some amount of magnitude, and from B to fixed line A, we have another inclined line which is respected to another bending moment due to the summation of these two forces. Okay, and then we just we will calculate how to calculate the shear force bending moment later. Before going that, I would like to explain one more example here. How to draw shear force bending moment diagrams. How to draw shear? Suppose we have a cantilever beam here. So A, B, C, D. At the B and C, we have a loads of 18 newtons and 16 newtons. So I'm just considering a section XX here. Which this section XX will be at a distance of X from the free end. Okay. Suppose we need to calculate the baseline here. This is the baseline. So from the point D to C, there is no any loads up, either upward, either maybe downward. There is no any forces. Okay, there is no any forces. At the point C, we have a force. So up to D, so from D to C, there is no any force. So the line will be same to the baseline. Okay, there is no any force. After the application of C, after the C point C, we have a 60 newtons. So it rises to 60 newtons. Okay, and from here to here there is no any shear force, there is no any point load here. Okay, so the space will be ideal, so shear force will be constant. Okay, from here to here adding one more point load will be there, 18 newtons. Okay, from here to here there is no point load, there is no load. Okay, so it represents constant. Okay, here whenever the point load acts at a particular point, at that particular point only the shear force will be raised. The remaining distance will be constant. Okay, UDL. So this is the point load, in the sense we can call it as a the SFD will be straight lines. If in case of UDL, the SFD will be inclined. Okay, if in case of bending moment, here also from C to D there is no bending, there is no force, and there is no bending moment also. Okay, why? Because there is no force, and from the point C to B we have a force 60 kilonewtons, 60 newtons. So from C to B we have to draw a inclined line. Okay, after the point B, some amount, another force will be there. Okay, another force will be adding into the count. So from here to here another force will be there. Some another inclined line will be there up to here 60. So the total will be the 200 Newton meter. So here we need to calculate the values. Up to now we have to aware about see how to draw shear force and bending moment diagrams only. And right now we are going to discuss about the values, how to know values. So if in case shear force diagrams, shear force will be C equals to 4 kilonewtons. Okay, here the C at the point C, the 4 kilonewtons here. Okay, between B and C, the shear force remains constant, and okay, from B to C, there is no shear force here. At a point B, S of W changes due to the point suddenly changes to from 4 to another 4. Okay, 8 kilonewtons. This shear force constant to the equal of 8 kilonewtons. Okay, from here to here, 8 kilonewtons will be constant. Bending moment C equals to 0. Okay, why? Because there is no distance here due to the bending moment force. Bending moment B and C at section XX. The distance x from free end is given by So minus W into X. I'm just considering a section XX here. Due to the 4 kilonewtons, we have a base some bending moment, and this bending clockwise bending moment will be negative. Okay, negative W into X. Okay, if in case of X equals to 1 meter, okay, if in case of X equals to 1 meter, the bending moment will be minus 4 into just to represent 1 as X minus 4 kilonewton meter. Okay, similarly, bending moment at the distance of X from the free end is given by minus W minus 4X minus 4 of X minus 1. I'm just considering that here. I'm just considering a section access here. Some textbooks are explaining very roughly. Okay, there is no that amount of describing. Very simply support. It is very simply to understand further. Here, some textbooks will be getting complex. Okay, this textbooks for the in case of bending moment, it will be little bit complex. Suppose how does it comes? Let me explain. How does it comes? Is suppose I'm just considering a section axis here. All the you need to calculate the all the shear force, all the bending moments will be at the x-axis will be 0. So we need to calculate the all bending moments. Suppose 4 kilonewtons into x, 4x, which is negative, and then minus 4 into this is the x. The overall length will be 1 meter. This is the x, and due to the and this is x minus 1. So 1 minus x. Okay. Here also mx minus the 4x minus 4 times of x minus 1. At a x equals 0. Therefore, bending moment at a equals to minus 4x 4 times of 3 minus 4 times of 3 minus 1 minus 12. So 4 3s are 12 and 4 2s are 8. So minus 20 kilonewton meter. Okay. At bending moment C equals 0. At bending moment B, the minus 4 kilonewtons will be there. Okay. Here at bending moment A, the minus 20 kilonewton meter will be there. Okay.